So, you're here watching this video. Hopefully that means you've already done your homework because this is going to extend from the skills from homework, but I wanted just to preview something for tomorrow. You're not gonna have to do anything with this because we're gonna practice this skill tomorrow. So, let's say I have two vectors. A is 80 meters east, and B is, 100 meters at 53 degrees north of west. And I want to find A plus B. Okay, actually, let's not make this 53. Let's make this 70. Okay. A plus B. So we know A plus B is R. So let's do this graphically first. So here we go. North, east, south, west. All right. Let's pick a scale. 1 centimeter is equal to 10 meters. This thing is going to go east and north of west, so it's east and this way. So I want to make sure I'm towards the side of the page. And I'm going to go north, so I want to make sure I'm down the page a bit there. Let's put in our reference line. So we're doing that effectively. Boom. All right, so here we go. I'm going to draw my first vector, which is 80 meters east. So we go an 8 centimeter long vector, a little long there, and that is vector A. Now, from the end of vector A, we're going to draw vector B. And so the first thing I'm going to need to do is measure an angle. Okay, and I need to measure a 70-degree angle northward of the west line. So here's the west, 10, 20, 30, 40, 50, 60, 70. Pop that in. And now let's draw our 10 centimeter long vector up there. Beautiful. And so that is vector B. Now I'm also going to label that angle there. That is theta B. That is our 70 degrees. So now I want to draw the resultant. The resultant should go from the beginning of the first to the end of the last. So the beginning of A in this case to the end of B. Okay, that's vector R. And here's the angle that vector R makes with the nearest horizontal, so I'll call that theta R. So let's find our answer. Here we go. I'm going to measure that. It's annoyingly just longer than 10. Okay. Looks like it's 10.5. So I'm going to get the magnitude of vector R is 10.5 centimeters, which by my scale is 105 meters. Okay, now I'm going to measure my R, angle theta R, and it looks like it's 10, 20, 30, 40, 50, 64. So theta R is 64 degrees. Therefore, vector R is 105 meters at 64 degrees, and this is going northward of the east line. Boom, my graphical method. Now, here's the thing. If I want to do this mathematically, what don't I have here? I don't have a right triangle. And so the goal here is to make this into right triangle trigonometry. Okay? So notice what's problematic about that? Well, A is pretty good because that's just along the axis, but this B thing kind of ruins us. And that's where components come into play. Because watch what I can do here. Let me sketch in the components of all the non-axial vectors. And these are just sketches. I'm not doing this formally. Right there, that is the part of B that acts horizontally. And that's the part of B that acts vertically. Same thing for vector R. So there you go. That would be the part of vector R that acts horizontally. And that's the part of vector R that acts vertically. So if you notice here, one thing that's very clear is the part of R that's vertical is identical to the part of B that's vertical. And that should make sense because none of A acts vertical, so the resultant relies in the y direction upon whatever B is doing vertically. But that's not true horizontally. If you know horizontally here is vector Rx. But if you notice, how do I get to vector Rx? That's vector A and then vector Bx added together. Or it's how much of A goes horizontally plus how much of B goes horizontally. Now, some people are saying plus, but it's minus. But I'm talking about a vector addition, right? Where we do the first vector, and then from the end of the first vector, we do the second vector, and the resultant goes from the beginning of the first to the end of the second. It seems like here that vector Rx is equal to the part of A that acts horizontally, which happens to be all of it, by the way, vector plus the part of B that acts horizontally. Now, if there were more vectors, it'd be plus Cx plus yada, yada, yada. And then Ry here is Ay plus By plus yada, yada, Cy if it happened plus yada, yada, yada. It just so happens that Ay, the part of A that acts horizontally, is equal to 0. So if I wanted to do this process mathematically, what I would need to do is find all the components of the vectors and then find the horizontal component of R, the horizontal component of Ry, or the vertical component of Ry, and then, because those two always form a right triangle, I can then do Pythagorean theorem. That's the logic talking through. So practically, what does that mean? Well, if we talk about our three methodologies for solving vectors, notice before when we did like R was equal to, we had R was equal to A plus B in our previous examples. We're never going to do that anymore because we always want to find just the components for each dimension first and then put them together. So when you have multi-dimensional problems, the best way to do these problems is with that table method that I was talking about. Here's where it's really powerful because it helps us organize our work. So if I look at this, so first off, we're doing this mathematical, I need to assign some directionality. Let's call east positive, west negative, north positive, south negative, right? So if I look at vector A and I say, well, how much of vector A goes in the x direction? Well, all of it does. So here we go, 80 meters. And it goes in east, which is the positive x direction. How much of vector A goes in the vertical direction? Well, east, none of it does, and I'm done. But if I notice here, B, part of it goes horizontally, part of it goes vertically. So what I'm going to have to do here on the side here is some side work to find out what the magnitude of the horizontal component of B is. And I know I can find that by doing the magnitude of B times cosine of theta B. Why cosine? Because if I come back to the picture, the x component of B is on the adjacent side. So let's do that plug-in. So that's 100 meters cosine of 70 degrees. I throw that in my calculator, 100 cosine of 70, and I get 34.2 meters, right? And while we're at it, I'm going to need the y component, so let's calculate that here on the side. And notice I always have an equation, I plug in with units, and I get my answer in units. Nice orderly structure to our problem solving. Okay, and so that's going to be 93.96, we're just going to go 94.0, okay, meters. Now I need to put them on my table. But here's where I need to make sure I'm using directionality. Because if I look at the x component here, that's west, so this has got to be a negative 34.2 meters. And then vertically, 94 meters, and it's a north vector, north is positive, boom. So now if I want to know the parts of vector R, I just add up the columns. So it's like I'm doing these two equations, but on a table format. So it's the same thing. Here, obviously, that's plus 94, and here that is plus 45.8 meters. Notice here this plus means east because it's x, and this plus means north because that's y, and that's helpful for decoding. So now that I know the x and y components of the resultant, the magnitude of the resultant is just back to what we did before. So knowing the parts of the resultant are how we put this together. It's just a little bit more complicated here because I didn't have a right triangle, and I had to make the right triangle. So here's 45.8 meters squared plus, just taking it off the table, 94 meters quantity squared. Throw that in our calculator. So 45.8 squared plus 94 squared equal to the square root of quantity. Good. 104.6 meters. And I need to have a direction. Theta r is equal to, if we look at that, adjacent, or rather opposite over adjacent, so it's y over x, right? So tangent inverse of ry magnitude over rx, and that's going to be tangent -1 of 94 meters over 45.8 meters. Plug that into our calculator. Second tangent, 94 divided by 45.8, and I get, oh, hold on a second, that was wrong. Second tangent of 94 divided by 45.8. What do I have here? Oh, I'm sorry, the mode on the calculator got changed because that was weird. There's clear all. Okay, let's try that again. Because I'm expecting, by the way, some angle between 0 and 90, and it should be greater than 45, just looking at our picture. So second tangent, let's try this again, 94 divided by 45.8. I probably was doing, yep, my parentheses. That was my problem. So 64.0 degrees. And then let's finish it off. Therefore, our vector r is 104.6 meters at 64.0 degrees. And then looking at this north of east, if I compare that to my graphical answer, it is magical, 105 meters, 104.6 meters, 64. It's great, it checks out. So this is going to be what we're practicing during our Zoom double on Thursday, is adding vectors irrespective of the angle between them using this chart methodology and making sure that we feel comfortable with this methodology.